We're going to briefly run through some of the facts about exponential and logarithmic functions that are outlined in section 11.1 of the book. But rather than have an assignment on that section, I thought I'd just run through and tell you the properties of these things that you need to know, and then we would do some examples from the exercises in 11.2 to illustrate the ideas. So briefly, we're going to talk about exponential and logarithmic functions. The term exponential function comes from the fact that it's a function where the variable in the function appears in the exponent, and this is as opposed to a function like something like we had an expression like like x squared. There is an exponent in this, but the variable here is not in the exponent. The variable is the base of the expression. So this is not exponential. This is a polynomial. We say exponential, we mean these guys where the variable, the letter, is in the exponent. Now you would have remembered this from your previous coursework that there are some basic properties of exponential and logarithmic functions, and some of them are not easy to remember. Some of them are. One thing that really helps, I think, for the exponential properties is thinking of exponentiation as repeated multiplication. So as you can see here, we're talking about this notation, number to a power. If we interpret the power as just the number of times we multiply the base, then 2 to the 5th is 32. E cubed is e times e times e. Remember, e is a number here. It's not a variable. It's 2.718, yada, yada, yada. We'll talk a little bit more about that in a minute. If you think of exponentiation that way, then the properties are actually pretty straightforward. So, for example, if we have 17 to the 4th times 17 squared, well, if you think 17 to the 4th in your mind, picture 4 17s being multiplied together, and for 17 squared, you picture 2 of these guys multiplied together, then all you have to really think about here is that if you have a string of 4 17s and 2 17s sitting next to each other, then altogether you have 6 17s. So it makes sense that the exponent would be added in this case because you're just stringing together 4 of the 17s with 2 of the 17s, making 6. The other rule that is a little harder for people to keep straight because it involves more exponentiation. It's an exponent to an exponent, but it's the same basic idea. If we had 17 to the 4th squared, well, the squaring means to repeat whatever's in the parentheses twice. So that means we have 2 of these because the original expression was 7 to the 4th squared. Of course, 7 to the 4th is 4 17s every time you see it. And so you have 4 17s, and in another group of 4 17s, you have that list repeated twice. So altogether, you have 8 17s. So it makes sense then that the number of 17s you have written down is 4 times 2 because you have 2 groups of 4. So these are the two basic exponent rules that we use throughout this course. What we really work with, though, are exponential functions, which means that we don't want to think about these things as just being evaluated with like 17 or something. We want to think about it as a function of x being evaluated for all possible x. So, for example, with 10 to the x, if I did f of -1, that's 10 to the -1 power, and we've talked about that with our calculus rules, that's 1 over 10, so that's 1/10, 0.1. So right there, when the x-coordinate is -1, the y-coordinate is 1/10. And similarly, we can evaluate this at any point. Don't forget that e to the x is perfectly good. E is not a variable. E is a number that's about 2.718. In other words, it's a number between 2 and 3, slightly closer to 3 than 2, but that's how we want to think about it. Notice that all exponential functions at a glance have basically the same shape. So the base here just really determines how steep this thing grows, but they all have pretty much the same shape. If we did go to our TI calculator, which I have plugged in, which is now off, let's see if I can wake it up here. In my TI calculator, I can enter a function, e to the x. So I would enter e to the x power. E to the x power. And then I would hit my graph button to see a picture of this. I'll take a second. So that's what my exponential function looks like. And then I can use the calc menu. Remember, once I have a picture on the screen, that's above the trace function, above the trace button on your calculator. So second trace brings up calc. Option 6 is the slope. And I can either put my cursor on a coordinate. So let's say I put my cursor on x equals 2, for example. And it tells me that the slope is 7.389, which is what I have written down in the table. On the other hand, if I use trace, not calc, which is regular trace, and tell it to make my x-coordinate equal to 2, and hit enter, then it tells me my y-coordinate is 7.389. So in other words, my y-coordinate and my slope are exactly the same. And that's exactly what happens for the e to the x function. If you looked anywhere on this picture and asked for the y-coordinate using trace or asked for the slope using the calc menu, you would see that the y-coordinate and the slope correspond at every single point. So what that means for us in terms of derivative rules is it means we have the world's easiest derivative rule if we have an e to the x in an expression. If I have e to the x in an expression, the derivative of e to the x is just e to the x. So even though you might not like e to the x as a function for a lot of the algebraic manipulation you have to do, from a calculus point of view, it is one of our favorite functions because it is really, really easy to compute a derivative for. In general, we can work with any base. The rule is slightly less nice for other bases, but we can still do it. So for example, the derivative of 2 to the x, well, it's just 2 to the x like it was for e to the x, but we get an extra number that pops out front. A natural log of 2, which we can calculate on the calculator, it's about 0.69 and so on, sort of pops out of the outside. So the derivative of 2 to the x is 2 to the x, but then times this extra factor.